Nearly 5,000 meters in darkness below the surface ocean, scientists have detected rising oxygen levels without any sunlight or photosynthesis. This phenomenon, known as dark oxygen, may be powered by metal-rich nodules on the seafloor, possibly acting like natural batteries. What does this mean for everything we thought we knew about life on Earth? Let's dive in. Deep below the Pacific Ocean, nearly 5,000 meters beneath the surface, researchers detected rising oxygen levels in sealed, lightless water zones. No sunlight, no plants, no photosynthesis, and yet, oxygen. This discovery challenges over 100 years of biology, which teaches that oxygen is only produced through photosynthesis. But in these dark waters, something else is happening. Something completely unexpected. Scientists believe unusual microbes may be behind it. These deep-sea organisms don't rely on light. Instead, they use unique chemical reactions to produce oxygen. Researchers are focusing on three key processes. 1. Nitrite oxidation, where microbes convert nitrogen compounds into usable energy. 2. Chlorate respiration, a rare pathway that breaks down chlorate and releases oxygen. And 3. Electrochemical reactions involving metals like manganese or sulfur, which might generate oxygen in complete darkness. This isn't just rewriting textbooks, it could reshape our understanding of life's origin. Could early Earth have been shaped by microbes using these same reactions long before the first plants? Evidence supports this idea. In 2021, a team working in the Clarion-Clipperton Zone found oxygen forming in sterilized, lightless water. Their results were confirmed in early 2025 by marine biologists off Africa's coast. Even more compelling, fossilized microbes found in South Africa's Barberton Greenstone Belt are estimated to be 3.5 billion years old, older than photosynthesis. These ancient life forms may have used dark oxygen chemistry to survive. Could dark oxygen be a living relic of Earth's first breath? The mystery runs deep, and it's only just beginning. In the year 2013, marine scientist Dr. Andrew Sweetman set out for one of the most remote places on Earth, the Clarion-Clipperton Zone. Located between Hawaii and Mexico, this vast undersea plain spans over 4.5 million square kilometers, making it larger than India. This region is scattered with polymetallic nodules, rock-like formations rich in nickel, cobalt, manganese, and other rare elements critical for clean energy technology. Sweetman wasn't chasing anomalies, he was studying the environmental risks of deep-sea mining. To measure oxygen levels on the seafloor, his team deployed sealed benthic chambers. The expectation was simple. Oxygen would slowly drop as microscopic organisms consumed it. But the opposite happened. Oxygen levels rose. Initially dismissed as sensor error, the anomaly reappeared in multiple chambers, 5,000 meters below the surface, in total darkness. No plants, no sunlight, no known explanation. In 2021, Sweetman returned, this time with updated instruments and strict protocols. Same site, different tools, same baffling result, oxygen increasing in darkness. This time, the data held up under scrutiny. By 2022, the Norwegian Marine Institute confirmed the findings, and in early 2025, the International Seabed Authority, supported by data from the Woods Hole Oceanographic Institution, validated it again, using high-resolution oxygen sensors and deep-sea vehicles. No equipment failure, no data glitch. Something real is happening at the bottom of the Pacific. If the source is chemical, it may change how we understand Earth's geochemical systems. If biological, it would mean life is producing oxygen without light, something we thought was impossible. And now the clock is ticking. According to a 2025 report by the World Ocean Review, industrial mining in the Clarion-Clipperton Zone could begin within 10 years. But if these nodules are part of an oxygen-producing system, disturbing them could damage ecosystems we haven't even discovered yet. This isn't just a mystery, it's a challenge to what we thought we knew about life on Earth. 5,000 meters beneath the ocean's surface, there is no light. This is the Clarion-Clipperton Zone. Remote, vast, and largely unexplored, it spans over 4.5 million square kilometers across the central Pacific between Hawaii and Mexico, an area larger than all of Western Europe combined. Down here, sunlight has never reached. Pressure is over 500 times greater than at sea level. Temperatures stay just above freezing, and the only sounds are the slow, seismic groans of Earth's crust shifting beneath the seabed. This region is marked by oxygen minimum zones, massive underwater layers where oxygen is nearly undetectable, typically found between 200 and 1,000 meters deep. Some of these zones plunge far deeper. But strangely, researchers are now seeing oxygen spikes where they expect depletion, especially near ridges and plains filled with polymetallic nodules. According to the Global Ocean Observing System's 2025 Deep Ocean Report, oxygen levels in parts of the eastern tropical Pacific are persistently deviating from expected patterns. Instead of falling, they're rising, defying long-standing ocean chemistry models. In 2024, Nigerian deep-sea biologist Dr. Lelo Ubasi joined an international mission into these depths. As her submersible neared the seafloor, she described seeing an electric blue jellyfish drift past. Then, something eel-like moved through the frame, its motion somewhere between a crawl and a swim. It was just one of hundreds of unknown species. Some looked like glass-bodied jellyfish, others like alien flowers with metallic stems. Despite their scientific importance, much of these deep zones remain unmapped. As of 2025, the Seabed 2030 project by the National Oceanic and Atmospheric Administration confirms that less than 1/4 of the ocean floor has been adequately charted. Even fewer areas have been biologically surveyed. And the deeper it gets, the stranger it becomes. From the Paru-Chile Trench to the Mariana, the Pacific trenches can reach more than 11,000 meters in depth. Yet, according to the Intergovernmental Oceanographic Commission, over 80% of the Pacific seabed has never been directly observed, making it more mysterious than the surface of the moon. But these aren't just geological trenches. They are scientific frontiers, places where ancient microbes may still survive, and where strange processes like dark oxygen might be quietly reshaping our understanding of life itself. Before we continue, I have a special 10-second request for all of you listening. If you can help me in any way, just press the notification bell and hit that subscribe button. It means the world. It really supports this channel. And if you do that for me, I promise my team and I will do everything we can to make this show even better for you. Most of us learned that oxygen comes from plants using sunlight. On land, trees and grasses absorb carbon dioxide and release oxygen through photosynthesis. In the ocean, tiny organisms called phytoplankton do the same. As of the National Oceanic and Atmospheric Administration's Global Oxygen Systems Report, phytoplankton are responsible for between 50 and 80% of Earth's total oxygen supply. But here's where it gets interesting. Phytoplankton need sunlight. They live only near the ocean's surface. Sunlight fades after 200 meters. By 1,000 meters, the ocean turns completely dark, and by 5,000 meters, it's permanent night. So how does oxygen reach those depths? The answer begins at the poles. There, frigid winds cool surface water until it becomes dense enough to sink. That cold water, now rich in oxygen from the atmosphere, begins a slow descent. As it drops, it becomes part of a global circulation, a deep underwater conveyor belt carrying oxygen across the world's oceans. According to a 2024 study by the Woods Hole Oceanographic Institution, this full journey takes nearly 1,000 years. It is the only known way for oxygen to reach the deep sea, which leads to a critical insight. The oxygen found in the Pacific's abyss today likely began its journey centuries ago, near Antarctica or the North Atlantic. But now, scientists are seeing something that shouldn't be possible. Instead of oxygen gradually decreasing as animals and bacteria consume it, measurements show that oxygen is increasing 5,000 meters below the surface, in total darkness, with no sunlight, no photosynthesis, and no known source. That changes everything. If the only known oxygen source is surface water that sank hundreds of years ago, and if that oxygen should be slowly disappearing, then something must be creating new oxygen down there. If oxygen is rising 5,000 meters deep, without sunlight, plants, or polar currents, then something else is producing it. That mystery led scientists to a groundbreaking idea. Dr. Andrew Sweetman and his team proposed that polymetallic nodules found across the Clarion-Clipperton Zone might not just be mineral lumps, but natural batteries. These nodules, shaped like potatoes and buried in the sediment, form over millions of years as metal layers build around a tiny core, often a fossil shard or shell fragment. Rich in manganese, cobalt, nickel, and iron, they contain materials known for conducting electricity. According to the Marine Minerals Report by the International Seabed Authority, nodules in the Pacific can hold up to 29% manganese oxide by weight, along with copper and rare earth elements, key components in modern energy storage. Sweetman's team wondered, could these metal-rich nodules under pressure, salt water, and the right sediment chemistry generate electrical energy? And could that energy drive electrolysis, splitting seawater into hydrogen and oxygen? To find out, the team sterilized nodules and sediment, sealed them in high-pressure airtight containers with seawater, and waited. Days later, oxygen levels rose. In collaboration with Northwestern University, they used ultrasensitive voltmeters and recorded electrical outputs up to 0.95 volts. Just below the 1.5 volts needed for electrolysis, equivalent to a standard AA battery. That means a rock on the ocean floor, under pressure, in complete darkness, may be generating enough energy to produce oxygen. Not through life, not through light, but through mineral chemistry alone. If Earth's crust can generate oxygen this way, it challenges core assumptions about the role of biology in shaping our atmosphere, and opens new questions about how life might arise on other worlds. What if we've been stepping over nature's hidden technology without realizing it? Could dark oxygen be the first sign of a deeper energy system beneath our oceans? Share your theories in the comments. We're always excited to read what you think. After Dr. Sweetman's team proposed their radical hypothesis, there was only one path forward: test it. Aboard the research vessel Pelagia, anchored above the silent expanse of the Clarion-Clipperton Zone, the team got to work. They collected fresh samples of polymetallic nodules and surrounding sediment. These were no ordinary rocks. Each one had taken millions of years to form, with metals slowly layering around fossil fragments beneath the seafloor. To eliminate any interference from microbes, the samples were fully sterilized using high-pressure steam and radiation. They were then sealed in glass containers, filled with cold, filtered seawater, and kept in total darkness. Over 6 days, oxygen increased by as much as 6.2%, according to data published in the Journal of Oceanic Chemistry. This wasn't a one-off. Repeated tests using multiple containers showed the same trend. To rule out contamination or sensor error, the team partnered with the Northwestern University Center for Electrochemical Analysis, one of the most advanced marine chemistry labs in the United States. In a lab simulating deep ocean pressure, salinity, and temperature, researchers connected sterilized nodules to ultrasensitive voltmeters. The readings were unmistakable. That energy, even in small amounts, would be enough to drive electrolysis, splitting seawater into hydrogen and oxygen, molecule by molecule without light and life. In early 2025, two independent research teams from the Tokyo Marine Science Institute and the German Max Planck Institute for Chemistry replicated the experiment using different models and seawater profiles. Both confirmed the results: stable voltage generation, oxygen spikes, and clear signs of electrolysis. As a result, the World Ocean Scientific Council now classifies these nodules as active geochemical contributors to abyssal oxygenation. This isn't a curiosity, it's a breakthrough. Oxygen, the foundation of life, can be created without any life at all. Up next, we ask a big question. If these nodules are really this important, what happens if we destroy them? Explores the ecological and ethical stakes of deep-sea mining. Once thought to be just mineral debris, deep-sea nodules are now central to a global scramble for the metals driving the green revolution. Found in large quantities across the Clarion-Clipperton Zone, these metallic spheres contain cobalt, nickel, and rare earth elements, crucial for electric vehicles, wind turbines, and smartphones. As of 2025, more than 30 exploratory mining licenses have been issued by the International Seabed Authority, covering nearly 1.5 million square kilometers of seabed. But as the push for extraction gains momentum, new research suggests these nodules may be far more than metallic resource banks. They could be biological keystones. A study by the Geomar Helmholtz Center and the University of Cape Town revealed that over half of all visible microbial life in sampled areas was either growing on or clustered around these nodules. Many of these microbes are linked to chemical processes that may contribute to oxygen production in some of the ocean's most oxygen-starved regions. Removing nodules, researchers warn, may dismantle ecological systems we've barely begun to understand. Marine ecologist Dr. Ali Matandi explains that nodules act as biological anchors. Dislodging them could unravel entire food webs, from microbes to scavengers that rely on them for survival. And recovery is painfully slow. A long-term study spanning 26 years found that test mine zones had regained less than 12% of their original biodiversity. Meanwhile, global demand continues to climb. Cobalt demand alone is projected to quadruple by the year 2030. Proponents of deep-sea mining argue that seafloor extraction leaves a smaller footprint than land-based operations. But scientists caution that the deep ocean remains one of Earth's least studied environments, and we still don't know the full consequences of disturbing it. Now, standing at the intersection of clean energy and deep-sea science, one urgent question remains. Should we mine forward to meet rising resource needs, or pause until science can reveal what we risk destroying beneath the waves? New research from the University of Pretoria, published in 2025, suggests this is a real possibility. According to the study, ancient microbes may have produced oxygen deep in Earth's oceans as far back as 3.8 billion years ago, when the surface was still bombarded by deadly ultraviolet radiation and largely uninhabitable. This theory turns the spotlight toward astrobiology and the icy moons of our solar system. Beneath the cracked ice of Europa, the erupting geysers of Enceladus, and the methane-thick atmosphere of Titan, scientists believe hidden oceans could exist. Oceans with no light, no photosynthesis, and yet, possibly, life. By 2025, missions and remote analyses confirmed the presence of hydrogen, carbon compounds, and geochemical activity on these moons. Together, these ingredients suggest that similar chemical reactions, possibly including the dark oxygen process, could power alien ecosystems in complete darkness. But this discovery comes with a caveat. For decades, scientists have treated oxygen as a key biosignature, evidence that life might exist on another planet. However, the report by the NASA Astrobiology Institute warns that oxygen doesn't always mean life. It can also arise from purely chemical, non-living processes, so the presence of oxygen may no longer be enough. It might hint at the possibility of life, but not confirm it. As we expand our search for life beyond Earth, our assumptions must evolve. Because what we're learning now is clear. Life may not need sunlight. It may begin in the shadows. Could life thrive without sunlight right now on another moon or planet? Could the same forces that make oxygen deep in our oceans be quietly powering alien ecosystems? Let us know in the comments below. And don't forget to subscribe and follow the channel to discover more interesting things. At the Massachusetts Institute of Technology, researchers at the Center for Bio-Inspired Materials are now developing what they call biomimic batteries, sustainable micro-power devices modeled after polymetallic nodules. These systems use non-toxic metals and salt water. According to the ocean-inspired designs, outperform traditional prototypes under high-pressure conditions, with potential applications in underwater sensors, autonomous deep-sea robots, and even long-life medical implants. Yet the ocean's influence on innovation is expanding further. Synthetic biologists are now studying the microbial processes behind dark oxygen to rethink how oxygen could be generated in sealed environments. A review by the Synthetic Biology Global Network highlights projects in the United States, Japan, and Germany that are engineering marine microbes to replicate deep-sea respiration. The goal? To build compact, self-sustaining oxygen systems for space missions, deep-sea submarines, disaster recovery operations, and remote habitats where traditional life support fails. Meanwhile, the World Energy Council's Clean Futures report now includes biogeochemical electrolysis. An energy process modeled on deep-sea chemistry is one of the top emerging innovations in clean power. Though still experimental, it shows potential for developing scalable, low-emission energy systems on land. Altogether, these developments mark a turning point. For centuries, we've designed technology to control nature. But discoveries like dark oxygen suggest that nature may have already solved problems we're only beginning to understand. As of 2025, the National Oceanic and Atmospheric Administration estimates that more than 80% of Earth's oceans remain unexplored, not just unmapped, but completely unseen. Incredibly, we have more detailed data on the surface of the Moon than we do on the depths of our planet. And now even the most cautious scientists agree, the deep sea is not just full of possibilities, it is full of probabilities. Deep-sea biologist Dr. Anya Lopez of the European Marine Research Alliance put it bluntly, "If the deep ocean were a book, we've only read the first few pages. Within those unread chapters lie hydrothermal vents spewing metal-rich fluids, sulfur-consuming tube worms, and entire ecosystems built on chemical reactions rather than sunlight." According to the Global Ocean Biodiversity Initiative's review, less than 1% of deep-sea species have been identified. Many may rely on exotic metabolisms, including those tied to dark oxygen chemistry. This scientific frontier also reopens long-dismissed questions. Legends of submerged cities like Atlantis or Lemuria and glowing realms beneath the sea were once dismissed as myth. Today, some researchers suggest these stories may have originated from misunderstood natural events, volcanic vents, bioluminescent organisms, or unexplained underwater sounds. Even government agencies are paying closer attention. Unidentified submerged objects, or USOs, have appeared in naval logs for decades. In response, the United Nations Office for Outer Space Affairs recently called for greater transparency in sharing underwater surveillance data, citing both scientific value and safety concerns. Of course, speculation must not replace science, but history shows us that many once ridiculed ideas, like plate tectonics, deep-sea vents, and now dark oxygen, were eventually proven true. If you enjoyed today's video, please give it a like and don't forget to subscribe to the channel. Your support means a lot to us. Click on the video that appears on your screen right now. I hope you'll love this content. Comment below about the next topic you'd like to see featured on our channel. Thank you so much for watching, and we'll see you in the next video. Thanks for being with us. Leave a comment, like to show your support, and remember to hit that subscribe button for more exciting videos. See you next time.